Hello. In this video I'm going to explain a particular case of the estimation problem, which is the case where the joint distribution of the input and the target variable is Gaussian. Okay? So we will start with reminding the estimation problem. Our goal is to design a system that we call an estimator that, given an input x, produces an output s hat that is expected to be close in some way to the value of some target variable s. So s is the target, and x is usually called the observation or the input to the estimator. Well, the solution of the estimation problem in general will depend on the criteria we use to decide when an estimator is better than other. Okay? In this video we will be mainly focused on minimum mean square error estimation, which means that we will set as a goal to minimize the expected value of s minus s hat given square. Okay. Well, the general solution to this problem is what we usually call the mean square error estimate, which is known to be equal to the expected value of s given the observation. So this is the general solution to the estimation problem that can be applied to any particular distribution model. Okay, so well, this is the context, and in this video we're going to discuss what happens when the joint distribution of the random variables s and x is a Gaussian distribution. So our basic assumption is that s and x are two random variables with a joint distribution which is Gaussian, with a mean that is a vector composed by ms and mx, and some variance which can be defined by blocks as the composition of the variance of s, the covariance of s and x, and the variance of x. Okay. So this is our general case. We will assume that in this case both s and x can be vectors. So we will assume that s can be a vector, an m-dimensional vector, and x can be an n-dimensional vector. So both can be vectors and with different dimensions. Okay. So, well, all these parameters of the Gaussian distribution have a statistical interpretation. Ms is the expected value of s, mx is the expected value of x, vs is the variance of s, vsx is the covariance of s and x, that is the expected value of s minus ms times x minus mx transpose. This is capital S. And Vx is the variance of x. Okay. So this will be our basic assumptions, and our goal will be to find the expected value of s given x, that is the minimum mean square error estimate in this case. Okay. So how can we compute the posterior mean? Well, in this case, and in general, in order to compute the posterior mean, we need to compute the posterior distribution of S given X, and then compute the integral of S times the posterior distribution. So we need to identify the posterior distribution. Well, by looking at the joint distribution, and the posterior is computed at the ratio of the joint distribution the ratio of the joint distribution and the marginal distribution. Okay. The marginal distribution is known because the marginal of any Gaussian distribution is Gaussian 2, so we know the denominator x is just a Gaussian random variable with a mean which is mx and a variance which is vx, the same parameters that we have here. It's just are just subcomponents of the mean and variance of the joint distribution. So we know the numerator and the denominator in the expression of the posterior distribution, and well, noting that the denominator does not depend on S, does not depend on S, we can see that the marginal distribution is just a proportionality factor over the joint distribution, but it doesn't change the shape of the joint distribution as a function of S. Therefore, if the joint distribution has a Gaussian shape as a function of S, the posterior distribution will have a Gaussian shape too. Therefore, we can be sure, we can assert that the posterior distribution of S given X will be also Gaussian with some mean and some variance that we don't know, but that we could compute. Okay? So in order to characterize the posterior distribution, we just need to compute the mean and the variance. Okay? I will skip the details. We can do that. We know the formula for the joint density, and we know the formula for the marginal distribution of X. So we can just replace in this expression, in this ratio, the joint distribution of the marginals by the corresponding formulas, and just make some algebra just to identify what is the mean and what is the variance of the resulting posterior. Okay? Well, this process takes a lot of algebraic steps that are a bit cumbersome, so I will skip the details. I will just show the solution after some algebra. You have the details of the in the one-dimensional case in the book, so you can check how that would be done. But I will show here just the solution. It can be shown that the mean of S given X is given by the mean of S plus the covariance of S and X times the inverse of the variance of X times X minus MX. And the variance is given by Vs minus Vsx times Vx to the minus 1 times Vsx transpose. Okay? And you, well, both equations are interesting. Well, the first we can say is that once we have the ms given x, ms given x is the mean of the posterior distribution, so this is the expected value of s given x, and this is exactly what we were looking for. Therefore, this is the estimator that we were looking for. Okay, so the parameter ms given x is exactly the formula of the estimator that we have been looking for. The distribution is Gaussian, and the Gaussian distribution has a particularity, is that the mean, the median, and the mode of the distribution are the same, and this implies that the maximum a posteriori estimate and also the minimum mean absolute difference estimate are also given by the same equation. So, well, we have solved the estimation problem in under different criteria in a row. Okay. Another interesting consequence of this expression is that ms given x is a linear function of x. Okay. Looking at this formula, it depends on several parameters, but as a function of x, this is a linear function. So an important consequence of the estimation in the Gaussian case is that the optimal estimator is a linear function of the observation. Okay. So this is one of the great advantages of the Gaussian distributions, is that we have an explicit equation for the estimator even in multidimensional cases, and the estimator is linear. Okay. And the variance is interesting too, because we have an explicit equation for the variance in the multidimensional case, and well, the variance is just a way to measure, is a form to measure the uncertainty on the value of the target variable s after the observation. So the variance is an interesting measure on how much uncertainty do we have about the true value of the target variable after observing the input. Okay.